Next is crown ethers. Crown ether. Crown ethers are macromolecular polyethers. Macromolecular polyethers. That means these are large ring compounds containing more than 12 carbon atoms and a large number of ethereal oxygen atoms arranged in a regular pattern. So, crown ethers are macromolecular ring compounds containing more than 12 carbon atoms and many ethereal oxygens arranged in a regular pattern. So look at here, example for crown ether. Okay, another example. Okay, these are a few examples of crown ether. So crown ethers are, so as I told you, crown ethers are large ring compounds containing more than 12 carbon atoms and many ethereal oxygen atoms arranged in a regular pattern. So these are examples of crown ethers. What is the name of this crown ether? This crown ether is known as a 12 crown 4 and this is 18 crown 6 and how you get the name of this crown ether? Look at that, the first number 12, it is the total number of atoms present in the ring. That means look at it here, 1 2 3 4 5 6 7 8 9 10, 11, 12. So total number of atoms present in the ring, that is this first number, and this 4 is the number of oxygen atoms, 4. Okay, so this is 12 crown 4 and look at here, the next one, how will you get this name? So look at here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Total number of atoms in the ring is 18 and crown 6. Number of oxygen atoms 1, 2, 3, 4, 5, 6. Crown 6. Okay. So this is crown ether. Now next is applications of, that is important, application of crown ethers. Properties and application of crown ether. Properties and application of crown ether. First one, these crown ethers can make complex with positive metal ions known as inclusion compounds. That means it can make this crown ethers, crown ether can make inclusion compounds. That means it can make complex with metal ions. It can make complex with metal ions, metallic ions. This is due to the cavities present in the crown ethers. So crown ether can make complex with metal cations. Why they can make complex with the metal cation? Because in crown ethers you can see that in crown ethers there are many vacant spaces, and in these cavities they can take this metal cation, they can absorb on the metal cation on the cavities present in the crown ether. Okay, and that means the crown ether is acting as the host and the cation is the guest. In such a way they can make a inclusion compound. Therefore these properties can be used for the separation of cations in a mixture. So first one, look at it here. Crown ethers can make inclusion compounds, that means complex with metallic ions, metal cations. This is due to the presence of cavities on the surface of the crown ether. To these cavities the metallic cations are adsorbed. That means crown ether is acting as the host and the metal cations are the guest. This property can be used for the separation of metallic positive ions in a mixture, because metallic positive ions in a mixture, what will happen by the application of crown ether? What will happen? The metallic positive cations, positive ions will be adsorbed on the cavities of the crown ether. So this way we can separate the metallic ions in a mixture. That is the first application. Second one, it can be used as phase transfer catalysis. Can be used as phase transfer catalyst or catalyst, phase transfer catalyst. Okay, can be used as a phase transfer catalyst. Okay, look at here. What is this one? Phase transfer catalyst. We can see that reaction between aqueous KMnO4 and organic substance in organic solvent is accelerated by a small amount of crown ether. That means, what is that? Example is reaction between aqueous KMnO4 and organic substance. Okay, organic substance. The reaction between aqueous KMnO4 and an organic substance in organic solvent. The reaction is taking place in organic solvent like benzene. Suppose the reaction is taking place in organic solvent like benzene. What is the reaction? Reaction between KMnO4 and organic substance. Okay, that reaction is taking place in organic solvent like benzene. So what will happen? In organic solvent like benzene, only the organic substance will dissolve and the KMnO4 will not. That means the rate of reaction is very slow. But when you add a small amount of crown ether, we can see that the reaction is very much accelerated. The reason is that the crown ether will dissolve KMnO4. That already we have discussed what will happen. The crown ether will separate these K plus ions, or the crown ether will dissolve the K plus ions, and hence you can see that the crown ether is dissolving KMnO4 or K plus ion, and the organic solvent is dissolving organic substance. By that way, the crown ether can maintain a homogeneity between these two phases. That means aqueous phase and organic phase. Clear? So in organic solvent, only the organic substance is dissolving, KMnO4 will not. But when you add crown ether, what will happen? The crown ether will dissolve KMnO4 and thereby maintaining a homogeneity. Between the aqueous phase, this is aqueous phase, and the organic phase. That means the mixture will become homogeneous. Okay, so the two compounds will mix together. That means there will maintain a homogeneity. Okay, that is the second application. Now the third application, Crown ethers are used for the resolution of a racemic mixture. Separation of so third one used for resolution of racemic mixture, resolution of racemic mixture. This is the third application. What do you mean by resolution? Resolution is the separation of racemic mixture into their DNL form. Okay, so used for the resolution of the racemic mixture. Fourth one, to complex phenol, amines, etc. And the last application is the for nucleophilic substitution reaction. Nucleophilic substitution reaction. It is used for nucleophilic substitution reaction. Look at here, C6H5CH2Br plus KF in presence of crown ether. You can see that this Br, this nucleophile is immediately substituted with fluorine, C6H5CH2 EF. So this is nucleophilic substitution reaction. So crown is used for the nucleophilic substitution reaction. Another example is CH3COCl plus KF in presence of crown ether. CH3COCl plus KF. You can see that the Cl will be immediately replaced by fluorine, CH3COEF. So this type of reaction we use crown ethers. So these are the application of crown ether. Now next topic is epoxides. Epoxides are three-membered cyclic ether. Three-membered cyclic ether. Three-membered cyclic ether. It is also known as oxiranes. Epoxides are also known as oxiranes. Three-membered cyclic ether. Example, ethylene oxide or ethene oxide, three-membered cyclic ether. Okay, another example. This is also three-membered cyclic ether. Another example is this one. So this type of compounds are known as epoxides. Okay. This is cyclohexene oxide. So epoxides are three-membered cyclic ether. Okay. Preparation. Epoxides are also known as oxiranes. Preparation. By the epoxidation of alkenes. That means when alkenes are treated with per acid, like per-benzoic acid, per-acetic acid, etc., we get epoxides. So alkene with alkene with per acid, like example per-benzoic acid, per-acetic acid, etc. So look at here, CH3, CH double bond, CH2 propane react with per-benzoic acid. How will you write per-benzoic acid? C6H5 CO2OH. Per-benzoic acid. So C6H5 CO2OH means actually CO2 benzoic acid is COH. Okay. Here you can see that benzoic acid is C double bond OH, and here you can see that OOH. Okay, this is per-benzoic acid, C6H5 CO2OH. This is per-benzoic acid, or simply you can write this one is C6H5 CO2OH. What is this one? Per-benzoic acid. Per-benzoic acid. perbenzoic acid. Okay, we get look at here what we get, CH3 CH single bond CH2, and here it is oxygen. Okay, propene oxide. What is this one? Propene oxide. This is the method of preparation of epoxide. Okay, one more example. Okay, look at here. Suppose this is your compound. Okay, react with C6H5 SO2 or CO2 OH perbenzoic acid. What we get? We get, okay, here it is like this, and here it will become oxygen. Okay. Now next is reactions of epoxides. Reactions. Acid catalyzed. The first type of reaction is acid catalyzed reactions. Acid catalyzed ring opening reaction. Acid catalyzed ring opening reaction. Number one, look at here, ethylene oxide. Okay, react with acid hydrolysis, H2OH plus, we get CH2, this side also OH, and here also CH2OH. Glycol, ethylene glycol, first reaction. Second one, CH2, ethylene oxide, react with ethanol, C2H5OH, ethanol, we get CH2OH, CH2O, C2H5. Okay, third reaction, CH2 ethylene oxide, react with HBr, we get CH2OH, CH2Br. Okay. Now, second type of reaction is base catalyzed ring opening reaction. Base catalyzed ring opening reaction. Base catalyzed ring opening reaction. Okay, look at here. Ethylene oxide, number one, ethylene oxide react with water in basic medium, OH metals. You get the same product, CH2OH, CH2OH. Okay, second reaction, ethylene oxide react with ammonia, NH3. We can write H, NH2, so we get CH2OH, and here it is CH2NH2. Okay, third one, reduction, CH2, ethylene oxide, CH2O, to reduce with the hydrogen, that means in presence LiAlH for lithium aluminum hydride. When reduced with the lithium aluminum hydride, you get CH2OH, CH3. We get ethanol. So these are the important reactions of ethylene oxide, that means epoxide. Okay, so that's all about this unit. Thank you.